What's up guys, it's me again. We're going to continue with this mass balance course and especially with this Gibbs phase rule. Probably you know the name Gibbs from the free energy of Gibbs or Gibbs free energy. It's the same guy, but this time we're going to see something about phases. And yes, let's continue. If you don't know, we're talking about mass balance. We're in MB3, which means we are in multiple phases. We're doing multiple balance, we're mass balance with multiple phases. And yeah, before I enter into the definition, I just want to make clear this intensive concept. The properties in a system could be either intensive or extensive. And it's so easy. Intensive doesn't depend on matter or the quantity of matter. And extensive actually does. For example, mass flow. An example of intensive quantities are temperature. It doesn't matter if you have 1 kilo or 10 kilos, the temperature will be the same. The specific volume or density of the substance also is not dependent. You can have 1 kilo of water and it will have the same density as 10 pounds of water or whatever. And eventually also pressure. We can also talk about compositions. It doesn't matter if I tell you I have a composition of A and a composition of half B. No, sorry. You have 10 kilos of this is the same as having 100 kilos because the concentration doesn't change. But for the other side, extensive quantities do matter. For example, mass flow. If I tell you it's being fed at 100 kilograms per hour, that's extensive because if I say 10 kilograms per hour, it will of course affect the mass balance. Also, volumetric flow is a extensive quantity, and we have others. But right now we're going to see just intensive variables. And let's go to the definition. The number of intensive variables, I told you before what these are, that can be specified independently. This is very important. Independently means that we need equations not dependent for a system at equilibrium. So we're talking about a system that is in equilibrium. So let's talk again. The number of intensive variables that can be specified independently for a system at equilibrium is given by this formula. dF or DOF means degrees of freedom. Remember that if we have 0 degrees of freedom, we have our system set. Equals 2. This is later I will tell you where does these 2 comes from. Actually, in the thermodynamic or equilibrium thermodynamic course, you will see that. C is the number of chemical species. It's adding, because when you add, you are adding more equations. And the number of phases, that's subtracting, because when you add phases you need more specification, more temperature, pressure, etc. So this is right here the equation. We're going to do some examples so you can understand how does it work. And yeah, as I told you before, when you have a zero system with 0 degrees of freedom, you have a definite or set system. You have 1 degree of freedom, you gotta say either, I don't know, a pressure or a temperature or a substance or a, I don't know, a phase, whatever. Now let's do some exercise so you can get this a little bit more clear. They tell you please determine the degrees of freedom. I like to call them DOF. Probably in your book you will see DF. Of each of the following systems at equilibrium. They gotta be in equilibrium, guys. If you're not in equilibrium, then it will not work. Specify a feasible set of independent variables for each system. Okay, so pure liquid water, it's normal, liquid, it's liquid, it's at equilibrium, but it's still water. And it's pure, we have no substances extra. So C is easy to get, it's just one, it's water. One substance. And how many phases do we have? We only have liquid phase, so we choose 1 here, and we simply substitute. It's 2 plus 1 minus 1 will give you 2. So essentially, if I tell you liquid water or pure liquid water, I will tell you please tell me the vapor pressure, and the temperature to set it. Okay, yeah, let's continue. We're going to talk also about this mixture of liquid, which is liquid and a solid and a vapor, but it's only water. So let's say we have, probably it's a triple point, I don't know. You have water, you have a solid, and you have vapor. Number of substances or compounds, it's only one, water, so we choose one here. Number of phases is of course 3, liquid, solid, and vapor, 3. So we substitute this, we got 2 plus 1 minus 3 should give you 0. So we don't need to specify any temperature nor pressure, because actually I told you before it's a triple point, you got only one triple point, so you want to be in equilibrium, you only, and I tell you there's a liquid and a vapor and a solid phase, you are sure you're in this point and you got your pressure and your temperature. So that's cool, because probably if I tell you please tell me what's the pressure and temperature, I will get liquid, solid, and vapor. Many people will tell me please tell me just the temperature or the vapor pressure so I can find it, and you don't actually need it because the system is already set and we know there's only one triple point. So cool, let's continue. A vapor liquid mixture of acetone and methyl ethyl ketone. So guys, just to let you know, this is only one compound plus the other acetone compound will give you 2. So this is here 2. No, 2 compounds. Now they tell you it's a vapor liquid mixture, so it's 2 phases. And yeah, just substitute, and we will need, of course, if I tell you there's a mixture, hopefully you've seen these diagrams of mixtures, you need to set, of course, a pressure or a composition or a temperature. Because if you don't set one, if you only set pressure, you could have infinite, well, not infinite, but a lot of compositions with the X value and different temperatures, of course. All different temperatures with different X's or mass or mole compositions. So what about, let's make a conclusion. It's interesting, but actually it's not that difficult. So if you get this problem, you will be able always to get how many variables you need to set in order to get a system well defined. It's helpful to determine the variables in the system. So for example, I tell you you need to specify 2, probably there are 3, and as you know, you have 2 variables, you can get the other one. Or in the case of the triple point, you don't need to, you maybe have these 3 guys, but you don't need either of those because you know you're in the triple point. Or sometimes you will have, I don't know, composition, a lot of variables, and if you set only one, you will be asking yourself, where do I get the other specifications? So this will help. The Gibbs phase rule will tell you when to add or when to search for more equations or to set variables, because if not, it will be impossible for you. If they tell you, for example, liquid water, what is the boiling point, you will need to ask me, of course, at what pressure. If I don't set you the pressure, you will have a line, which means a lot of values with that boiling point. So yeah, as we were telling before, sometimes we will actually have to set the points ourselves. Suppose, for example, they don't tell you the pressure, but I don't know, they tell you probably it's atmospheric pressure, so you set it to 1. Or if you're making a balance and you know the tower pressure, probably you can use that pressure. It depends on the problem. So for example, we have this diagram, and if we wouldn't have fixed pressure to 1 atmosphere, we will have a lot of diagrams, because we will have actually a 3-dimensional diagram in which every cut, for example, this is 1 cut, this will be the pressure axis. Let's say this is pressure, and it starts with 1, which is our phase, like the cube phase. But then if we go another little bit behind, like let's say 2 atmospheres, hopefully you get this is kind of tricky because it's 3-dimensional. But if you go a little bit behind, you will get another cut of the cube, and so on. You will make, I don't know, let's go for 5 pressure, 5 atmospheres, and then you can go for 10 atmosphere. Every cut you make, imagine this is like a bread, and you're cutting each loaf of bread, and each loaf of bread will have a different diagram. So it will be very complicated to show this cube. Actually, you could show it in different. You could show pressure 2, pressure 3. But why will we want to do that? If we're working in different pressures, it makes sense. But we know we are working with, I don't know, distillation column with a constant temperature. So why not just ignore all the other pressures, because we know it's constant, and we will make our effort here. So let's set the pressure to 1, and we get a simple two-dimensional diagram. Hopefully you get it, guys, and if not, don't worry. Actually, this is more of thermodynamic and equilibrium thermodynamics, but it will be nice if you understand it right now, so it will be easier for you to understand in thermodynamics. Now, in this case, you will probably see that we have different pressures, different temperatures, and probably different volumes like these. And you will ask yourself, what are we setting? What you probably didn't see here is that we have a composition, which means we have to set substances or substance composition. But here right now, guys, we have one substance only, which is water. So C turns into 1. In this case, probably C was 2 because it's binary. And the phases, we have 2 phases. Let me put it right here. Actually, let's do the... So you got to set 2 plus 2 minus 2 will give you 2 variables. I already set one variable, which is pressure, and I'm going to let free temperature and x. Because if I give you one temperature, which is the thing you're going to set, I don't know, probably say, well, I already set temperature, pressure. Now let me set pressure, temperature here. I want to set it to 100. At 100, you will have only one data here. And as I told you before, you set pressure and you set temperature, you will have your system well defined, and you will find only one value of that. So let's come here. It's one, no, we have actually 3 phases. We have 2 plus 1 minus 3 phases. You will have a well-defined system. So you have everything here, guys. Critical point. You just need to choose a pressure, a temperature, and you will find it. So hopefully you're getting the idea of why here we don't need a 3-dimensional, because we don't have more data, or more, we have 0 degrees of freedom, we don't need extra info. So we only need to fix the substance. So yeah, that was the thing I wanted. Oh yeah, the last thing I wanted to tell you from Gibbs phase rule. It's by fixing a property, let's say pressure, volume, or temperature, you will reduce this three-dimensional chart. For example, the one we were watching right now was pressure, y-axis, and temperature, x-axis. Let's go back. You can see it's pressure here and temperature here of substance named water. So what we are actually doing is we're choosing one volume, which probably will be, I don't know, we'll choose 1 cubic meter per kilogram or kilomole. So we choose one volume, I don't care which one, probably you will choose one. And what we are going to do is the same, like if it was, let's see, there's a cube, sorry about the drawing. So let's say we have this cube, it's like a bread, and we're going to make this loaf, which is the volume we're interested, because actually we don't care that much in volume, we're studying pressure and temperature. So just let me make this look two-dimensional. So if you were watching from here, you will see the x-axis as a temperature and the y-axis as pressure, and you will see all these lines which are in depth. You will see them in a two-dimensional array. So let's say you take a picture from here, you take a picture of what you see here, and you will see actually this here, guys. You will see a line here, you will see another line here, and this line here. So probably it's kinda, here's the straight line of the solid liquid, you see it from here, the vapor line, this is the solid line, and the equilibrium, and the critical point is here. So hopefully you're getting, let's say, because it's two-dimensional, we could say this line transfers to here. So hopefully you're getting the idea, guys. This is the solid vapor equilibrium we have here. We have the liquid here, and we have the liquid vapor equilibrium, which is essentially this. So that's in the case we choose a, how to say, a volume or amount of quantity, for example, cubic meters. But what if we choose to set one pressure? Let's say pressure atmospheric. We will have the same stuff here, but we will now be watching, let's say, from the top. I'm going to watch from the top, and I'm not going to show you diagrams, but you will see, imagine the loaf of bread is here. You will see a two-dimensional diagram here. And what if we choose, I don't know, let me just take it away. What if we choose to set the temperature? So that will mean that we will need to be watching from here. Let's say temperature. We set a temperature, let's say this temperature. So you will have pressure versus volume. This is pressure, and this is volume. This is pressure, of course, and this is also volume. And you will have very nice, actually you will see this diagram, which probably we will be seeing. You have this kind, they call this the bell of liquid vapor, and you have solid liquid. And this is very typical for thermodynamics. You want pressure and temperature, so you can get to see how the volumes and pressure interact between each others. Yeah, that's what I wanted to tell you guys. If you don't understand, it is so abstract, don't worry. This is typical for thermodynamics, but you will get an idea of how they work. So yeah, we're going to make this slide the end of this section number 1 of MB3 multi-phase mass balances. So far we've seen single phase theory. So what are the phase diagrams? We've seen normally the pressures and temperature. We're going to use this axis. It's not always this axis. I told you before, you can choose whatever you want. This could be your x-axis, this could be your y-axis, this could be your x-axis. Yeah, actually also there are also temperature versus volume. This could be your y-axis and temperature, whatever. So we've seen also the equilibrium lines, which are very, very important. It's the way they approach or interact between solid, liquid, and even solid vapor, and of course liquid vapor. We've seen critical point, which is the point at which we cannot differentiate the phases between liquid and vapor. We've seen also triple point, which is the point where the three lengths get together, and the only point in which we can have the three phases at the same time or at the same conditions. And of course, what's a phase? Now, we've seen also a little bit about vapor pressure, which is the measurement of volatility, and we've seen how to calculate it with Koch's diagram, which is very, very easy. The Antoine empirical equation, which is pretty accurate, and the Clapeyron theoretical equation. I like it like theoretical because the name says it is a theoretical approach. It's kind of okay. Antoine equation is better, but it makes you understand why are we getting these lines or these equilibrium lines as straight lines. And of course we saw lastly the Gibbs phase rule, which is the intensive variable analysis of a system. We will need pressure, temperature, composition, whatever. So given the number of components and the given of phases, you will need to set some kind of variables. So yeah, next video we're going to see section 2, which is essentially gas liquid system for one condensation component, and gas liquid system for multi condensation, which is very interesting for distillation. So hopefully you're understanding everything, guys. You got doubts, just send an email or review the chapter, and see you in the other video. What's up, guys? It's me, chemical engineering guy. So if you like the video, why not push the like button? It really helps me to know if you're liking the videos or if I should be changing something or I should be adding something, taking out content, whatever. Also, sharing is caring. So if you got any kind of friends, teachers, colleagues, or whatever kind of person that might be interested in this type of content, why not share it? Sharing helps our community to grow faster in members and in content. If you want to keep track of my activity, videos, uploads, experiments, playlists, whatever content I'm getting on YouTube, be sure to click the subscribe button. Subscribing to the channel is totally free, guys. My dream is to create an online academy of chemical engineering, where everyone can access it in the world. Imagine a place in which the student, the teacher, and the engineer get the best of each other. So thank you guys for the support and the love.